Now, when you're talking about chemistry, you have to realize that atoms are really, really small. All right. And I'm not just talking really small, I'm talking really, really small. So if you go to the sink right now and you let about a teaspoon of water go down the sink, intentionally or unintentionally, that teaspoon of water has more molecules of water in it than there are teaspoons of water in the Atlantic Ocean. Now, let's just think about that for a second. Atlantic Ocean is big. If you haven't seen it, it's like the Pacific Ocean. You can't see Europe or Africa or anything like that. It's a big, big ocean. And if you were to go out there with a teaspoon and, go 1 scoop, 2 scoop, et cetera, there's a lot of teaspoons. I mean, a lot of teaspoons. However, your teaspoon of water that you put down the drain has more molecules in it than there are teaspoons in the Atlantic Ocean. So, wow, atoms are small. If there's that many molecules in a teaspoon, then that must mean they are not just small, they're freaking small. So in chemistry, we have to use different ways of thinking about the world because what we see may not be what's happening on the small level. So I'm going to talk sometimes in this class about macroscopic, and that's just the world of what we see and do. That's the cell phone world. That's the world of when you go get something to drink from the refrigerator, the things that you and I see in our day-to-day world. But we're also going to talk about what's usually called atomic, but sometimes called microscopic world, and that's the world of atoms, all right? Because sometimes we have to visualize what's happening on this atomic scale to understand some of the things that are happening in the macroscopic scale. The reason I try and stay away from microscopic is actually bigger than atomic, and microscopic is more the world of biology. But anyway, it is the same thing. It's a very, very small world, and we'll have to shrink ourselves down in the terms of chemistry to the level of the atom to make sense of things. And finally, sometimes it's useful to talk about the symbolic world, and that's just using symbols and nomenclature to understand and talk about what's happening with colleagues, all right? Because it's hard to visualize something and share that visualization with another person. But if you use symbols and you use ideas that are common to converse with your colleagues, then you can start making sense. Sharing ideas is what makes the world go around.
A balloon filled with hydrogen and surrounded by air represents a potential chemical reaction. To initiate the reaction, we need to ignite the balloon. The hydrogen will combine with oxygen in the air to form water in gaseous form, releasing considerable energy in the process. At the molecular scale, the molecules of gaseous hydrogen, H2, and oxygen, O2, combine to produce H2O, water, generating heat and light.
So this is kind of a great overview of the three different domains and what they represent. Now, first of all, in the upper right-hand corner, when you saw that little balloon exploding, what was happening is inside the balloon, you have hydrogen. And when hydrogen has a little bit of a flare, basically a spark, if you will, it can ignite with the oxygen to make water. And it's a lot of energy is released, and you can hear the boom kind of thing right there. So that's the macroscopic world. All right, that's what's happening when you and I watch this reaction happening. But you might think, wonder what exactly is happening on that level, Dr. Russell? Well, great question, random student. In the left-hand corner, you see the atomic representation. So on the atomic level, inside the yellow balloon there, you have the white atoms, and those white atoms are hydrogen. And we'll talk more about why this is the case later. But hydrogen comes in pairs. Right now, that's all you need to worry about. And hydrogen then, when you have the spark, the hydrogen then ignites, and outside the yellow balloon are those red molecules, pairs of molecules once again. That's oxygen. And again, we'll talk about what's all happening here in a little bit. But anyway, the hydrogen, when ignited, reacts with the oxygen outside. A lot of energy is created, and you end up making water. So in the lower screen there, you've got the red oxygen atom between the two white hydrogens. That's water, H2O. And that's what's created. And in the process, a lot of energy is given off. So atomic level, that's what's happening. The little pairs of hydrogens are reacting with the pairs of oxygens to make the pairs of water. Notice that kind of V structure for water. We'll talk about that later this quarter. That's for a future lecture. But anyway, now if I'm going to refer to this when I'm talking to you outside of this video, I don't want to try and describe pairs of oxygens and hydrogens, blah, blah, blah. So in the lower right-hand corner is a chemical reaction, which is a symbolic way of representing how this works. And as it turns out, you're going to need 2 of those H2 molecules to react with 1 O2 molecule to make 2 H2O molecules. And the G there stands for gas, so that tells you what the final phase of this stuff is. You can see there's an arrow, so to the left is kind of like what you start with. We'll call it the reactants. To the right is what you end up with, the products. That's the symbolic representation. So in chemistry, all of these perspectives are important, and we'll use them interchangeably sometimes to describe the things that are happening. This is an example showing some different phases of water. You can see actually well, you can't really see them, but anyway, you can, on the macroscopic world, all right, you see the ocean, you see the big iceberg kind of floating there and stuff in the water. And even though you can't see it, all of the air we breathe has water in it, water vapor. So you're seeing all 3 versions of water. You're seeing it as a solid, which is ice in the middle. You're seeing it as the liquid water in the bottom. And even though you can't see it, the air does have water gas. And then at the atomic level there, you can see in those circles, you can see that gases are actually kind of spread out while the solids are kind of close to each other in wild forms. And in liquids, they're close to each other, but it's a little bit more random. So again, this is just another representation of the ways that we'll use this quarter to talk about chemical reactions and what's happening.